Hey everybody, welcome once again to Astronomy Daily Live. So hope everybody's doing well out there in the universe and the world. I've got a shedding kitty on my lap that just decided to jump off and go explore other pieces of the universe. So hope everybody's doing well out there today. Everything's good here. It's just crazy windy here, but that's pretty typical for this time of year in the springtime here in the desert southwest of the United States. The wind blows. So that's pretty normal as far as that goes. It's always very strong, and sometimes when it's cold, it just penetrates, right? It just goes right through, right down to the bone, and yeah, so that's how it is now, and it's just crazy. It's completely clear otherwise, which is kind of a bummer because with this strong of a wind, no telescope time at all. The telescope is just going to jiggle around way too much, and that's all I'll get is just smeared out objects. And I got something in my eye too from this wind. Yeah, so hope everybody's doing well out there. The Falcon Heavy launch was postponed. I noticed one more day, so I think tomorrow might be the day. Might be. Who knows? They just have to keep trying. With everything like that. The conditions have to be just about right, and there are certain parameters that have to be met, and so when those aren't met for whatever reason, they have to stand down and try again, the next day, and I don't know, I don't know how far along they got in the process today. Hopefully, they didn't try to fuel or anything, but sometimes they go that far, they get it all fueled up, all ready to go. They're about to push the button, and it's like, nope, too windy, or nope. There's some kind of condition wasn't met, and they have to stand down. They have to detank. They gotta, but that's how it goes. We like these kinds of things, as with all of our travels. We want them to be successful and pretty uneventful. Just sort of get there. You can definitely enjoy the ride as you go, but the whole point is to get there. So I am grabbing my chat here, just sort of babbling along, letting everybody come on in. This is just very much a casual, fun get-together of a ever-growing group of friends each and every day, talking astronomy and space and science and nerdy things. So hope everybody's doing well. All's well here. Just sort of a normal day. Hope everybody's doing well out there. So without further ado, Bobby, hey, what's going on over there?
Nothing much. I was thinking about we might be able to look at those papers today.
Well, I am very much a and I forget the term, but you know, if mostly everybody is doing this over here, I want to do this over here. So I'm gonna not do much with the black hole stuff at this point. I definitely want, you know, to let everybody know that there are 6 papers out describing the entire process that they went through, all the instrumentation, all the methodology, all of that. What they did, they collected this data 2 years ago, and so they've spent the past 2 years just wringing this data out, and they came up with a result, interesting result, but you know, you know. Yeah, okay. So, you know, the high priests have now spoken. It's like, you know, here it is, and everybody, of course, is you know, extremely exciting, and you know, hyperventilating over all of this, and my thing is, you know, I'm going to look at the papers and run it through the scientific process. All right, so don't get excited yet. I think, you know, if they've done, you know, what they say they've done, it is pretty exciting, and but it requires you some scrutiny. Part of the problem with these kinds of projects is you know, one of the steps that's vital to the scientific process is verification, is you know, to find another group to sort of repeat the experiment and see if they get the same results. Well, how do you do that in this case? Can you do that? Right? Different instrumentation, different telescopes, different people. I don't see that happening. So you know, it's hard to do science on these kinds of things where you can't repeat the experiment. But you know, you can look at the process and see, you know, what they've done, and you know, if it passes muster there, then it looks good. So you know, I mean, it's extremely exciting. But yeah, I would definitely encourage you all, even, you know, even if you're absolutely certain that you are not going to understand a thing about it, right? It is gonna just fly way over, right? I mean, that's what it's going to do with me, for the most part. But I'm going to look at these things and say, okay, you know, what can I try to understand about this? And you know, does it make sense to me? What they were doing, you know, is really complicated. It's really hard, you know, to do what they did, and so you know, that alone is a major accomplishment. And I hope that they use this technology, you know, to do other things too. You know, because the capabilities of that kind of a thing are absolutely stupendous, right? You know, the resolving power of the you know, series of instruments they used is 2,500 times the resolution of the Hubble telescope. So just absolutely fabulous. Great stuff. But yeah, I'm not going to spend too much time on that because that's what everybody else is doing. I'm going to go do something else. So
I guess
anyway,
I'm going to go where they're going to do something else. There is,
yeah.
There is one thing that I did notice. I watched the press conference that went on for an hour. And one of the things I noticed that was notably absent from it, as an American, I watched this thing, and there was no U.S. presence of any kind at all. It's like the United States didn't exist, and I guess that shows you where we are about now in science and contribution there too. It's really kind of sad.
Yeah, well, there were something like 6 press conferences going on simultaneously. So, and I don't remember exactly where those were, and I don't remember which one I watched either. But
I watched the one that was published on Deep Astronomy because I follow that channel.
Okay, yeah, that's actually exactly the one I watched too, and I don't know where they were. I'm not exactly sure where, but yeah, you know that at least the panel I saw, you saw exactly the same one. It was all Europeans, which is great, but most definitely, the United States played a major contribution in this. If nothing else, the instrumentation, right? One of the telescopes they use is just to the north of me here. So the United States was definitely involved, and I'm absolutely certain, if you look at the list of the members of the group, there's going to be a lot of Americans on there. But yeah, kind of interesting, and like I said, extremely exciting, really cool. But let's not get too excited yet. Let's look at the data, look at the methodology, see what they did, and I think probably the only surprise is that everybody thought that it was going to be the center of our galaxy that they looked at, and no, it wasn't. It was the center of another galaxy, massive galaxy, Messier 87. Beautiful galaxy, in fact. If you have a scope, oh wow, you can see that galaxy, I think, at a dark site, maybe with a 6-inch, maybe even with a 4-inch scope. It is bright, it is big, it's absolutely gorgeous.
Oh yeah.
Big elliptical galaxy.
Even with my 5-inch Sky Prodigy, which isn't my good scope, I can see M87.
Excellent. Great. Yeah. So Atta, how are you doing over there?
Really well.
Good.
Hey, I noticed you got a ponytail. I thought you was like an alien at first, but no, you got a ponytail.
I have ears. No one's noticed my ears.
Oh, she's got the ears.
I have.
Oh, she's got the spots. She's got the spotty ears. She's got the spotty ears.
Now, did you?
She's a Spock.
Did you come that way, or did you have those things installed?
I have these great ears. I had them installed. My hair isn't. This is my real hair. My real hair is steel gray. It's not white, and it's very long. It's up in a big wad on top of my head. Nice. I have that white hair I wear because I fit in better around here with it.
You just haven't run out of ink yet. That's all.
That's it. Oh, yeah. Oh, wait. I shouldn't be laughing with my ears.
That's right. You could hurt somebody with those.
Okay. So Uncle Bill Duran had a point about U.S. and EU. U.S. institutions have a big part of it.
Amen.
And I noticed it was all EU hype myself, but it's not like we aren't guilty of the same attitudes at times. They did release the image of Secretariat A afterward eventually, Ted larger but fuzzier, and like to welcome Chuck Nagel in the chat.
Hey, Chuck. All right, an ear lover. Good.
Excellent. An ear lover. Yes. That's great.
I'm
That's
trying to give
great.
this show a little panache, a little
well,
pizzazz.
It definitely needs it. It definitely needs it because I am one of the most boring dudes you'll ever know.
Oh yeah, so boring.
So
little panache.
All right. Well, cheers, everybody. This is the hydrogen hydroxide again, and wow, I filled this up, and somehow it's already gone down by almost half. So, yeah, hopefully we don't get into crisis situation here of any sort.
I got some faucet water. It is right about here, so I'm about to have a crisis as well.
Oh, all right. Well, we'll just have to wring our hands a little bit and just take it a little bit easy with that stuff today. So, all right.
Yeah.
Well, excellent. All right. Well, yeah, everything's good here. Like I said, it's clear here, but the wind is blowing like crazy, so nothing doing in terms of that department. So yeah, like I said, definitely take a look at those papers. Even if you don't understand it, like I say, look at the pictures. The pictures are great. Look at the captions under them. See if you can get anything out of it at all. It is, historical.
Sure.
So yeah, it's part of my background with astronomy is the high resolution imaging. So I'm always very, very excited to see these kinds of things. The diameter of that donut is 40 micro arc seconds. So just to give you a perspective on how small that actually is, okay? The moon is 1/2 of a degree wide, the full moon. Okay, that's 30 arc minutes. Okay, there are 60 minutes in 1 degree, and so this is half of that, so 30 minutes. Okay, in each arc minute, there are 60 arc seconds. Okay, so what does that mean? The moon is what, 1,800 arc seconds across. Okay, so they're talking about 40 micro arc seconds. That's 40 millionths of 1 arc second. So that it's just an incredibly small thing. And I haven't done the math, but it takes a telescope about the size of the Earth to get that kind of resolution, because that's really small. So that is amazing.
After all, with a smaller moon.
Oh yeah, yeah. That kind of accomplishment in and of itself, regardless of what the object is absolutely remarkable, right? That's absolutely fabulous. I wish they could turn that telescope to just a regular old star, because you'd be able to see sunspots with that, or star spots, easy. Yeah. Extremely exciting. Really great stuff. I'm anxious to see how exactly they did it. How they combined all the images together, and did this, because it's like I said, it's a major effort. And it's taken this huge team, right? Huge team, like two 2 years to get this out. So a lot of work, thousands and thousands and thousands of hours. So my hat's off there, definitely. That is definitely a great accomplishment, for sure. Absolutely. So cheers to that.
No wine or anything, Otto?
What? I didn't hear that, Bobby.
No wine or water or anything?
Sure. I have a mix.
All right. Excellent.
There you go.
Excellent.
Oh yeah.
There you go.
I drink the hard stuff.
All right.
Yeah.
Good for you.
I don't mess around.
I don't care where I go, whether there's alcohol or not. I just don't drink it all.
I didn't figure you did. My uncle was a member of your church, completely turned his life around. He used to be a heller and a drinker and running around. He turned into a wonderful family man, never touched a drop. So,
Yeah,
amen,
nice.
amen.
Yeah.
Yeah.
Well, I always encourage responsible use of anything.
Yeah, me too.
Yeah, I mean, as long as you're not being dumb about things, we're adults. We can handle ourselves. So enjoy yourself, whatever it is. I don't care what it is. Just don't be stupid about it. That's
Whatever
all.
it is, old age is going to kill me long before this does.
Now,
Very,
you're
very
in
likely.
Lancaster, Pennsylvania. I'm trying to spell it. Here we go. Let's see if there's.
What is Bobby looking up?
I don't know.
Oh yeah.
Something.
Oh yeah. All throughout Lancaster, you got like 3 meeting houses all around Lancaster.
Oh yeah.
Oh, okay.
One in Lebanon. Let's see. I'm trying.
This is a seriously religious area.
Yeah. There's the Lancaster, the Epatra ward. And it doesn't tell you if it's English or Spanish or combined and stuff. I know, like, if you search for meeting houses in Montreal, they'll tell you if it's, like, English or French or something like that.
Probably English here. This is a pretty provincial.
Because my branch is English and Spanish.
Cool. And there's Uncle Bill in the chat talking about Romulan ale.
Oh yeah.
And I'm reminded of the fact that even Spock. I don't remember what episode it was. I'm trying to remember what episode it was. But even Spock drank some alcohol at least once.
Yeah, he got really zinged on it. I remember that episode.
Yeah, I don't remember which one it was though.
I think everybody got a hangover on Star Trek 6.
Yeah. Yeah, I have some Romulan ale. It's blue stuff.
Oh, nice. Get that shipped over the.
And I take Star Trek 10 Nemesis. I take during the reception. Pretty much somewhere around the beginning. I know it began with the Romulan consul getting killed and stuff, and then they transitioned to that reception. I think Lieutenant Worf got drunk too much Romulan ale. He just said Romulan ale should be illegal.
Yeah. Well, alcohol and I have never gotten along at all. I don't like it. It doesn't like me. So we just sort of, parted ways, and it's like, have fun over there. So
Yeah.
Good for you. I'll drink to that.
Yeah, absolutely. Cheers.
Good for you.
Now, can you actually buy Romium ale today? Or what kind of stores or something like that does have Romium ale?
No, you can't buy it. You have to get some alcohol and put some. What I did was get some rum and put some blue coloring in it. And it comes across looking very much like Romulan ale, and it's got quite a kick to it. But you guys wouldn't drink that stuff, so.
Obviously, you all don't have the kind of connections I do, because I can get it right through the neutral zone, no problem whatsoever.
Oh!
I know a guy. And no problem at all. But I'm just not in the market for it. So That's great. That's great. Well, the other night I was observing, and one of the targets that I had planned on looking at and didn't was a planetary nebula called the Eskimo Nebula, and that's up in Gemini. And ever since then, I don't know why, I've been thinking about it. So I sort of wanted to take this episode to sort of dive into that and see what's up with that, and look at the Sinbad stuff and see what that's all about. You might be curious as to why it's called the Eskimo Nebula.
Looks like Tom and Scotter must have posted a link to. Well.
Oh,
well. $70.
Look at this.
Are you kidding me?
There you go.
$170?
Well, you got to smuggle it in from the neutral zone. That's a pretty good price. That's a pretty good price. So.
Oh yeah, they're giving it away, right?
Yeah.
$170.
That location, the experience is actually exactly the same place that I got this mug too. So yeah. The Star Trek experience there. I didn't know that was still going on there, but that is very, very cool. You get to stand on the bridge of the Enterprise. It's very, very cool.
What do they charge you for that? A couple $100?
I think it's, as I recall, it was very, very expensive. I don't remember exactly how much, but it sort of made me cringe a little bit. It's like, ooh, really? But
I'm going to make my own Romulan ale and compete with them.
There you go. There you go.
I'll sell mine for $100 a clip.
That's great. So, all right. Well, let's go over and take a look at the Eskimo Nebula. Of course, it's got an NGC number, but I don't remember what it is. So I'm going to look that up really, really quick here. NGC, of course, stands for New General Catalog.
I'll be right back. I have to get a refill.
All right.
Uh-oh. We just got our first crisis of the night.
First crisis of the night. Man, you can't run out of the drink. So that's just no good at all. All right, so NGC 2392. So let me get that loaded up here.
They got a Stellarium, regular edition of the Stellarium Mobile that I paid $3 on, and now they got a Stellarium Mobile Plus for $10.
Oh, I wonder what the plus is.
I don't know. I wonder if the plus is better than the original.
I don't know. All right, so I've got it loaded up into Sinbad.
It's the next generation storm mapping app combines a realistic and accurate night sky simulation with a gigantic amount of online imaging and sky object catalogs. The Plus version was assigned from the ground up to show a potentially unlimited amount of data through an intuitive and minimalist user interface. So it's got the Gaia, the DR2, planets and satellites, known deep sky objects, comets, exoplanets like minor solar system objects, visible artificial Earth satellites, including the ISS, full sky, very high multi-resolution background image. It's got a telescope control, and it can work without the need of the internet, but with a reduced set of data.
Yeah, cool. Yeah, you know, because they, you know, sorry about that. The star catalogs like Gaia, they're going to have to access that on the fly. I don't think that they're going to have, you know, to like have you download you know, the entire Gaia data set. That is gigabytes. So well, cool. Hopefully it's worth the $10. Sounds like a pretty good deal to me. So all right, I'm gonna go ahead and whoop. Why am I not? I froze. Oh, there we go.
That's not good.
What's with the potato tonight, huh? Here we go. All right, I'm gonna share. There we go. Oh, it's acting a little funky here, but we're gonna keep on going. So, all right, here is the Simbad page, and you know, the first first thing I see is this big white overexposed blob there. So we're definitely going to have to find a better picture of that to have a good idea as to why this might be called the Eskimo Nebula. So let me try to open up another window. Ooh, my poor machine here is really having trouble. So we're going to go over here and we're going to go to Eskimo Nebula, and we'll just go to the Wikipedia page because I just want to show you the picture. So, you know, this is a, let's see, you know, what we should do, because Wikipedia is always going to show...
The original Stellarium mobile app pretty much showed just about a couple of stars and stuff within about a few kilometers and stuff. So that's what it looks like.
Gotcha. Nice. So let's see. Can we find this anywhere where... Where are we? I'm not seeing any search anywhere here. Anyway, well, let's just move on a little bit. The basic idea is that you know, the Eskimo Nebula sort of kind of looks like an Eskimo face with all the fuzzy around it and all of that. This of course is a very overexposed image, which shows almost nothing. Let's see if this does a little better. Maybe it's not even there. Wow. Okay. I thought the cloudy nights would have that. Maybe I have to sign in. I can do that. Okay.
Yeah,
so nobody look. Here we go. All right, here we go. So let's look for Eskimo Nebula. This will hopefully show us a more sort of a realistic view. Here we go. NGC 2392, 4/16/19. So just a couple of days ago. Oh, so this is a sketch. Do we want to do a sketch? Let's not do a sketch. Let's do an actual image. Can we find one? Why don't we do search for 2392? Got to be stubborn when it comes to trying to find astronomical data of any sort. Astro video, first night. Here we go. Now, you know,
what on earth is going on?
These cats' jobs is to drop everything on the ground, and they're greatly accomplishing that. Everything must go onto the ground.
Use the men's room. I'll be right back.
All righty.
Yeah, look what Chuck said. He said, "Look up Clown Face Nebula." Maybe you should try that, Clown Face Nebula.
Okay. Well, here's one that's marked the clown. I don't know if I've ever heard it called that before. So, well, there's a relatively interesting view.
Well, I'm sure Chuck didn't just pick that out of the air.
Yeah. I don't know if I've ever heard that name before. Well, you know, this is a pretty reasonable view. Let's see what this. You have any info on this at all? No. Wow, not a lot of info about that picture. Let's see if we can improve upon that a little bit. Here's another one. 2392. There we go. That's moderately reasonable. The what you'll see in a telescope is of course, you know, this bright star, probably this bright star, and then, you know, surrounding it, you'll see a little gray fuzzy thing around that star. So, you know, just as a reminder, you know, this is a long exposure image, so never ever expect to see anything like this at all. With our own eyes, you'll never see, you know, this round part here. But with a relatively nice size scope, you know, like a 6-inch or an 8-inch scope, you can definitely see, you know, the planetary nebula here, and also what I think is the central star. I'm not quite sure if that is, you know, the central star of this planetary nebula, or if it's just some kind of foreground star that just so happens to be just dead center. I think it's more likely that is the central star of this nebula, and yeah, you know, it's just really bright. So, yep, there's the Eskimo Nebula in all of its glory. It's a nice nebula to see. It's as I recall, it's a little small, but let's take a look. Let's see what Sinbad has to say about it. Like I said, it's over in the constellation of Gemini, so it's definitely still up in the early evening. It's probably setting local time, maybe around like midnight or 1 a.m. or something like that. Let's see what else we can get out of this. This thing. So here's the position of it in the sky. Proper motions. Yeah, not a lot of motion there. Sort of expected. Radial velocity, it looks like it's moving away from us at about, well, they say 84.2 kilometers per second. So that's, you know, that's not a serious clip, but well, that's faster than I drive, so it's not bad. Not bad at all. So they're calling this an O6 central star, I guess. We'll have to dive into that a little bit more. O is typically very, very large and very, very bright and very, very hot. So yeah, not quite sure. We'll have to dive into that a little bit and see. But pretty bright in sort of the visible wavelengths. It's around 10th magnitude or so. And then as you move into the infrared, it almost stays almost exactly the same. You can sort of see that it's brighter in sort of the blue and the V filter here, and then fainter as it gets redder and redder. That's sort of typical for planetary nebulae. So pretty cool. Pretty cool. Wow, a bunch of different names. And yep, Chuck was right. There it is, Clown Nebula. All right there. So that is an official name. Oh, look, it's also called the clown face. So I don't think I've ever heard of that one either. So pretty cool. Nice. And just a bunch of other names that you know are usually from different kinds of catalogs. So you know, you're searching for some kind of a characteristic in a star or some kind of an object, and when you find that characteristic, it goes into your catalog. That's how that works. And so, yep, a bunch of different names, including NGC. Let's see, these are probably just the star names, right? Not necessarily the nebula's names. Yeah, lots of good stuff there. And of course, this has been looked at and researched quite a bit. Wow, so 686 references. That's a little bit for sure. Let's see what they're talking about in terms of how far away it is here and how it's moving. So a little bit of a discrepancy there. We got about 2,000 parsecs from one group and about 1,300 from another. So yeah, a little bit of discrepancy there. I think this 2018 one, I think that's probably Gaia. We can confirm that. Yeah, so this is Gaia data release 2. These guys, yeah, you know, we'd have to dive into the paper and see, you know, how exactly they came to that number. But yeah, there's a little bit of a discrepancy there, so we'll have to iron that out. Now, of course, these are in units of parsecs. So in order to get that to light years, you got to multiply that by 3.26. So I don't know. Should we just take the average of that? So 1998 plus 1259, and then I'll divide that by 2. So 1,628 parsecs, more or less. Yeah, you know, the error bars, look at the error bars on these things. They're really, really, really large. You know, so plus or minus 200 parsecs. So, but even that doesn't, you know, those two things still don't overlap. So yeah, there's a little bit of a discrepancy there. This doesn't say, you know, how they arrived at that. Like I said, you know, we'd have to look at the paper to really, really know. But we could do that if we wanted. But yeah, I think I'm going to skip that. So let's see. If we multiply that by 3.26 light years per parsec, you get 5,309 light years. So that's pretty darn far. That's not, you know, in terms of stellar objects, that's pretty far away. That's not insanely far away, but that's pretty far. Pretty far. So let's see. It looks like the velocities are sort of matching up. This one, those have got to be some kind of different units or something. I'm not exactly sure. These three agree so well, even from way back in 1953. Those numbers match really, really well. It's just this weird one here. So I'm not quite sure what's going on there with that number, but looks pretty reliable. So yeah, I'm moving away from us. That's what a positive radial velocity means. So yeah, all right. Proper motions, that's just how it's moving in the sky, right ascension and declination. And kind of scattered there too. So yeah, I like to look at these, because it sort of puts things in perspective in terms of how sure we scientists are about things, right? When you look at this kind of stuff, it's like, okay, well, how sure are we? I don't know. I don't think so, right? Yeah. And again, the references here, if you want to look it up and see how that was done. Again, it looks like this one from 2018 is definitely from Gaia. So that's sort of the latest and greatest catalog we have. Whether it's right or wrong, I don't know. Time will tell for sure. Parallax is a measure of distance. And again, we're there, wow, there's just a lot of discrepancy here. So, I don't know. You don't know. Kind of neat. All right, well, let's take a look at maybe what is recently being done with this object, and maybe we'll look at some early stuff too. In fact, why don't we start with the early stuff? I always start with the latest and greatest. Let's start with the earliest record that we have of the sky. Okay, so this goes all the way back to 1892, and obviously something in German. I don't know what that says. You could probably figure out a way to translate it, but I'm thinking that's probably not going to be necessary. Let's just look. Let's look at the pictures. Oh, it's being a little slow today. There we go.
Like I said, you know what? I only know a little French and a little English. I mean, no. I stand corrected. A little French and a little Spanish.
Ah, okay. Well, I sort of know English a little well, but man, I don't even claim to know that very well. So.
Well, everybody that's from around here should know English by heart.
Well, I don't know. Sometimes I'm not sure. So, all right. Well, obviously this is all in German, but let's see if we can get something out of this.
Ich spreche Deutsch ein wenig.
Yeah?
Yeah.
Do you have any idea what the title says?
I can't see it.
Oh, you can't?
No.
Try without your glasses.
I just see you. No, I just see you, Cosmic. I don't see.
Oh, am I not sharing my screen?
Yeah, you're sharing your screen.
Really, Bobby? You see what he's seeing?
Yeah. So I think what you gotta do is click on Cosmic's window, and you should be fine.
Oh yeah. Okay, I'll try that.
Try it.
I'm clicking on this window. Nothing's happening. Or whoops. No.
Try single clicking.
Okay. I'm going to try something completely different. I'll see in a few minutes and I'll be back. I have no idea what's going on.
All right. Well, I will.
Everything is. I clicked on some stuff, Bobby. Everything was working until I followed your advice.
All right. Well, let's see here. Let's see if we can make a little bit of sense of these things. Now, this is definitely right ascension and declination, epoch 1875. Right, so that's kind of cool. Oh, here's a general catalog number. I wonder if that is like the new general catalog number. 23. Oh, what is it? 2392. Well, I'm not. Yeah, it's hard to know if this is an NGC number or if it's something else. Oh, okay. It's not a numerical order. Great. Okay. Well, I didn't.
And I think this is like photocopy and digitized. Yeah,
I'm certain of it. So, okay. Yeah, I'm thinking that this may not be a new general catalog because that's a lot of. Oh, okay. Well, now hold on. I can definitely understand this. Planetary nebula right there. You see that? I can understand a little bit of that. Oh, but that's going into a different paper. So, man, I'm not sure. You know, we can go approximately by
version. I don't know why they didn't do a translation on that.
Oh, that's all right. Let's see. We could probably go by right ascension and declination. Now, the epoch is different, right? We're up to J2000. And because of the Earth's precession, things in the sky seem to move. But we should be able to find this. So 7.5 hours right ascension and almost 21 degrees. So let's see if we can find this 7. I bet you this one's it right here. Right? Because it's really, really, really close. 7:21. And like I said, because of precession, the right ascension and declination are going to be different. But 721 and plus 21, that seems to very, very closely match this. So I'm going to say that that's probably it right here, number 21. Now, I'm not quite sure what these other numbers are here. 3.55. and 7.005. Oh, it's in. Okay, well, this is some kind of unit of seconds and then seconds of arc over here. So this has something to do with right ascension, and this has something to do with declination. But yeah, I can't be sure. How's your German, Atta? Can you see that yet?
No, I am seeing it now. I'm looking here, see if I can make out anything.
Can you look at the title and see?
No, this is no, this is. Nah, I can't help you. This is too scientific.
Gotcha. Well, I'm seeing nebula here and some kind of measurement right? Because there's a meter at the end. So in fact, micrometer, right? Micrometer.
Yeah, micrometer. Some kind of micrometer.
Yeah. So
that's what they did the measurement with. Let's see.
Yeah.
Took in fun. No.
Yeah. All right.
No, I don't know.
Anyway, that's the earliest. Let's see if there was another early one here too that might have been at least in a language that we can understand. So 1901, the Astrophysical Journal, focal observations of the planetary nebulae and visual observations of Nova Persei with the 40-inch Yerkes telescope, which is now not used anymore. I don't even know if they're going to. I think they're still going to have an exhibit, but I don't think that they're actually going to be using it anymore. That was, and I believe still is, the largest refractor telescope in the world.
Oh my gosh.
So yeah, it's got a 40-inch lens right in the front of it. And so yeah, at least back in the day here, 1901, that was like the scope.
Oh yes, I remember it well.
Yerkes. Great scope. If they don't want it, they can send it over here. I'll take it. No problem. So let's take a look here and see what they're talking about. As is well known, the focus of the Large Refracting Telescope for the planetary nebulae is something like 0.25 inches further away from the object glass than for a fixed star. I don't know if I'm understanding that or not, but let's just keep going here. Natural consequence of the difference in the spectra of the stars and the planetary nebula. What? Are they saying that they have to refocus on the nebula as opposed to a star? That doesn't make much sense to me.
Seems like what they're saying. Let's see.
Oh, sorry.
Observations were determined. 40.
Yeah, that seems a little strange, but I'm gonna keep going here. So here it is, NGC 2392, and here's right ascension and declination epoch 1860.
So when did they came up with the first general class category, and then they came up with the NTC?
Well, I think that other catalog that we were looking at, with the German paper, that's some other catalog. I'm not quite sure. The NGC catalog has been around for, I think at least a couple hundred years, I think. So yeah, not quite sure. But yeah, those are definitely two different things. But yeah, look, they're talking about different foci for the nebula and the star in the case of all these planetaries. So I don't know what they're going with that. That doesn't make very much sense to me. So yeah. Anyway, that's an observation at least. Let's see if there's anything see if there's anything interesting here at all. Oh yeah. So 2392 is the Eskimo Nebula, and they say that it's the most remarkable of these objects. Okay, so here's, yeah, the bright star is 9th magnitude. A brightest ring, which is oval in form and almost incomplete in its southern part. The ring, well defined inside and out, surrounded by a vacuity. Not quite sure what a vacuity is. Okay, that's probably a gap. And yeah, so this is probably the gap they were seeing, right? So here's the central star, and then you have the inner part of the nebula, and then a vacuity, right? This darker region, and then surrounding that, they're talking about a broad ring of light, less intense, and with a distinct break in the north. That's kind of hard to tell. So anyway, yeah. So there is definitely an observation here of that object as seen through the 40-inch Yerkes telescope. I don't know if there's going to be any images or anything. Okay, and this is Mr. Barnard too. So he's a pretty famous astronomer. You've heard of Barnard's star? That's him.
Yeah. Oh yeah.
That's
him. Is Barnard mentioned in the Cosmos series?
Bobby, I don't recall. I can't think of any mention of him. So yeah, can't be absolutely certain about that. Okay, and then it goes on to Nova Persei, which is a very, very active star that keeps popping off, from time to time. So cool, very cool. All right, let's go over and look at sort of the latest and greatest when it comes to this object. Where's it going to land me? All right, it's going to land me at the front. Good. So let's just
lots of great papers from last year.
92. Yeah. Let's see if we can. So emission lines, iron 3 emission lines. So that's moderately interesting. A detailed kinematic model of that nebula. Okay. Let's keep going here. Abundances of planetary nebula NGC 2392. So they're probably just talking about the kind of stuff that they've actually found in there. So they're probably doing spectroscopy with this. Let's take a look. This is Astronomy and Astrophysics from 2008. Yeah, they're looking at spectra. So it's spectral analysis is probably some of the most useful means of gathering a lot of information about objects, because you can really dive into it and see what it's made of and what the conditions are, what the temperatures are, how much stuff there is, all of that. So okay, so they use Spitzer, which is a space telescope, obviously. I think Spitzer, I think Spitzer's looking in the infrared, if I remember right. Located in the direction of the galactic anti-center, so it's going away. So here, let's. Okay, so there's an HST image. Okie dokie. You can see this scale here. So this is 15 arc seconds. So it's relatively small. So you know when you look at this through your telescope, it's going to appear pretty small. It's almost going to look like a weird looking star at first, but you'll notice, you know, that it doesn't exactly look like a star. So all right, let's keep going here. I want to see some spectra. Infrared spectrum. Here we go. So here's a little bit, kind of scaled in a weird way, but they're seeing lots of ions: neon, silicon, sulfur, oxygen, iron, argon, and I don't know if you can see these little things here, but these are all what are called emission lines, or peaks. So and that's because, you know, this object is actually glowing. So, you know, it's shooting out all this light at these wavelengths. So as you can see, you know, this is in microns. So 10 microns is 10,000 angstroms. So this is very much into the infrared, actually the thermal infrared as they call it. Visible light would be way over to the left, way over there. But yeah, wow, you know, they're identifying, you know, very bright in the oxygen, and that's why, Atta, I think you have like an O3 filter.
Yeah, I have that. I have every filter you can possibly imagine. I even got that Radion light filter that that outfit on the West Coast is touting.
Oh, nice.
And they advertised it in Times Square.
Right.
Well, I figure if they could get images in Times Square, I could certainly get them in the parking lot on the roof of my building.
Yeah. You know, and that whole effort, trying to get, you know, the images from Times Square is an ongoing thing. They were able to see some stars, but yeah, that's about as far as they got. So
right. It was a little disappointing to me. I watched it, and it was a little disappointing because during the whole Times Square event, they were spending most of their time trying to get everything aligned with Polaris.
Right.
I mean, this is something you have to do wherever you are. It doesn't, and it seemed
like
there was very little time of actually observing. So I sort of bought this very expensive filter on faith. Right. And I've actually tried it once, and it is very good.
Wow.
I mean, it just takes out ambient. Any ambient light is gone. You know.
Yeah.
I mean, you know, it does do a good job.
Yeah. You know, the trade-off with these narrowband filters is that you either have to, you know, limit yourself to very bright objects, or you have to take really long exposures.
That's right.
Because you know, the narrow band means that not a lot of light is going to be going through there. So yeah, you know, that is sort of the limitation, but there are big advantages, to that, because you have at least the opportunity to see things from the middle of a city where you normally wouldn't be able to. So yeah, I think it's absolutely fabulous.
Well, light pollution isn't that bad.
Mm-hmm.
I mean, I do live in the country, but I wanted to be able to, since I have to keep my scopes at home now,
right.
I'd like to be able to. I can drive if I have to in this area where I live and find a dark spot. I mean, I am in the middle of the country, but dark is a relative term, and I wanted to get it as the best shot I could, especially for deeper space stuff. And this filter works well for that. I really don't need it for things like planets and close-up Messier objects, things like that. I don't need the special filter for that. I just go to a darker place,
right?
Which is easy enough to do where I am.
Nice. Anyway, yeah, they've identified lots and lots of stuff in this really, really bright line here.
Oh yeah.
So nice. Let's see what else they got here. 6 centimeter radio emission. So they even looked at it in the radio a little bit. Okay, so yeah, so here's some more IDs. Of course, hydrogen, neon, P. That's is that phosphorus? I think that's phosphorus. Is P? I don't know my chemistry all that well. What is P? Is that let's find out. Periodic table. We'll find out here. Just grab a picture of one. I don't know if is that going to tell us. Let's see how well this works. If I don't get into too much trouble. Can I see that? Here we go. Where is P? P is phosphorus. Nice. So they've identified phosphorus, iron, sulfur, chlorine 4. Wow. Yeah, just, everything, right? Pretty amazing. Lots and lots of stuff out there. Okay, so here's, yeah, they actually have some visible spectra too, it looks like. So we can definitely look at that. And here's your O3 filter right there, 5007. Those are the ones that I think are usually sold because it's really, really bright, and it's a nice color too. Let's see. I want to see some more spectra is what I want to see. IUE. So wow, they looked at this in the ultraviolet as well. So wow, they're really covering the wavelength range for sure. Be nice to actually see some spectra, but we're running out of paper. The central star. What are they saying that this central star is? Very, very hot. Between 40 and 45,000 degrees Kelvin. So that's a little warm. But yeah, that's sort of all over the place too. So it's hard hard to tell. You know, it depends on sometimes how you look at things. Not really seeing any other spectra. It's kind of interesting that they only show the infrared spectrum and not any of the other ones, but that's all right. Cool. Very cool. Let's see. Let's see what else we got here. I'm noting the time too, so I don't want to go too much longer, but it's always fun to dive into these a little bit and see what's up. Some old friends. I actually haven't looked at this object in many years, so I think this is definitely going to be near the top of my list the next time I'm out. I'm definitely in the mode of still trying to characterize my telescope and see how well everything works. So doing observations of this guy would definitely aid in that. So this is kind of an intriguing title, The Structure of NGC 2392. Let's look at that and then call it a day. So we'll go over to ADS again. Let's see what we've got here. Come on, little blue line. There we go. Extremely unusual spectrokinematic morphology. Several strange and elusive structures. Hey, I like it already. I love those words.
That guy knows how to write.
That's great. That's absolutely fantastic. That's the kind of abstract I like to read. Yep. That just pulls you right in, right?
It does.
You know? It's a hook.
Yeah. That paper's going to get accepted. There
you go. Yep. Narrowband imaging, right? So here's some narrowband imaging. We might be able to find out exactly how narrowband. So here's some O3 and S2 stuff. Okay. So let's see. They looked at this at a 1.5 meter telescope somewhere in Baja, California, Mexico. Cool. Nice. It was used to acquire 59 images. Why stop there? Let's see. So.
And you've been doing like 100, 200, and he's been doing 50?
Well, circumstances are different. So this is a 1.5 meter telescope, so they don't need as much as what I would need. That's much larger than what I've got, and so these things are light buckets. So the bigger the bucket, the more light they can grab. So that size of a telescope don't need a lot of data, to get some good results. So let's see the central wavelength. Let's see what we've got here. Okay, so here we go. So here are all the filters they used and their width. And wow, some of these are extremely narrow bands, 7 angstroms wide. Wow. So pretty amazing. You can see the exposure times here and the number of exposures they did. So even though the number of exposures is, I guess, what you would call low, what you have to do is you have to multiply this time by that, and then add all that up. And that's quite a bit of data there. So yeah, they're able to take some pretty long exposures, 2,720 seconds. Wow, that's let's see, 2720 divided by 60. That's 45 minutes. So yeah, they took 45-minute long exposures in 03. So yeah, that's some good data there for sure. All right, so here's some images here. So this is, I don't know if you can see that all that well. So here it is in 02 at 27 angstroms. So that's getting towards the ultraviolet. We can't really see things shorter than about 4,000 angstroms. So this I would definitely call sort of an ultraviolet image. I think we can still see those things. I mean, obviously, we can still see those things from the ground, but that's probably a tough one. 3727. Yeah, so a 1,200 second long exposure. Yeah, that sounds about right. So it's really amazing how different this object looks depending on what wavelength you look at it with. So helium-2 line, not incredibly exciting. I don't know if this blank area is real or not. Kind of hard to tell. But pretty uniform. Not a lot of structure there. But if you look at the oxygen 2 and the oxygen 3,
oh, God,
you can definitely see lots of structure in there. Very cool. Very cool. So here's just regular oxygen. Kind of cool. Yeah, I guess this is a real thing. I'm not quite sure. That's kind of neat that there's that kind of lack of oxygen right there in the middle. Here's hydrogen alpha, which is very, very red. That's around 6,300 angstroms or so. Does it say here? H alpha. Yeah. Oh, 65, 64. So, okay. And wow, they went all the way up to like 9,000 angstroms, which is very infrared. But that light can definitely get down to the ground. Oh, here's a little bit more. Wow, look at that. So nitrogen 2, look at that. Look at these spiky things, which it's just non-existent.
Oh yeah.
Here. Fantastic. So yeah, this is why looking at objects at different wavelengths is really revealing, because you can it's almost like looking at a completely different object every single time. So here's it looks like sulfur 2. Wow, kind of nice. Here's sulfur 3, so doubly ionized sulfur. Continuum is just that is looking at not any particular spectral feature. I don't know if they have any spectra in here. I think this is all imaging. Oh no, there's a little bit of spectra here. Oh, is that? No, these are actually profiles. So these are, if I'm reading this right, yeah. So these wiggly lines here, let's just take O3, the 5007 angstrom one here. So do you see that shape? What they've done, let's find the 5007 one here. Where is it? 5007. There it is. So what they've done is they've plotted the intensity of this sort of going across this way. So these, of course, are reversed images. So dark things or black things are actually bright, and white things are actually dark. And so you can sort of see it sort of gradually goes up, and then there's an edge where it jumps up here, and then it's pretty uniform, and then it jumps up again, and then it goes back down, and then up, and then down. So it's just a profile cut right across there showing the brightness of these things. And as you can see here, that's exactly what we're seeing here, is that, gradually here's that first little shelf part, and then here's that really, really dark area, right? Or bright areas, I should say. Here's the central area here. So yeah, cool. Nice. Nice, nice, nice. Well, come on up here if you want to come up in my lap. There we go. Now you cannot stand in front of the screen because I can't see it. All right, there we go. So electron density and temperature. Wow. Okay. Kind of cool. Electron density seems to be highest in this area. It's sort of the, I guess you'd call that the northern part. Yeah. Temperature doesn't really follow the density all that much. There's sort of similar structure here. Kind of cool though, right? To be able to measure the temperature or something that far away. Kind of cool. So yeah, these kinds of things. Well, I guess this is going back a little bit. What year was this? 1999. So yeah, 20 years ago. That's kind of interesting, isn't it? That it sort of looks like okay, yeah, right. We were just doing a search for that. So all right. Well, I think for now that should about do it. It's nice to see some old friends from time to time, and this is definitely an old friend of mine. Pretty cool to see all that kind of stuff. So when I get my data, I'll do exactly the same thing. I'm not going to have the resolution. I don't think that they have here. I think they said right at the beginning of the paper that they were getting like 0.4 arc seconds per pixel. My system at its best is about 1 arc second per pixel. So, this is twice the resolution that I've got. But, I would definitely, be able to do similar plots like this. So maybe I will see what happens. See how they compare. But yeah, nice paper. Pretty amazing object. Okay, yeah, you know, they're trying to understand, you know, the geometry a little bit here. What's going on? Pretty cool. Extended range of narrowband imaging. Maps of the temperatures. Revised model. Very cool. Good list of references there. Great. All right. Well, I'm definitely noticing that we're running a little bit long here, so I think I'm going to get on out of here. Let Atta turn back into a pumpkin, and I'm going to do exactly the same. So, all right, everybody, I'm going to check the chat really quick. I haven't been looking at the chat at all, so, but yeah, it doesn't look like there have been too many shenanigans, but good discussion over there, nevertheless. So, all right, everybody, take care. Peace, cheers, and all that. I will be back here once again tomorrow, 2 hours UTC. You know, if the there's a possibility that Astronomy Daily Live tomorrow might either be late or yeah, I don't think I have to cancel it. It might just be a little bit late because I think the Falcon Heavy launch right now, at least the last I saw, was set to launch at 1:35 UTC or somewhere around there. So that sounds sort of like an overlap of sorts. So I guess we'll sort of have to play it by ear and see how that goes. You know, if it looks like it's going to be delayed or canceled or anything, fine. But yeah, I think we're going to have to play it by ear. You can probably, unless it's canceled relatively early in the day, I think this live stream will probably be postponed until after the launch, because I definitely want you all, you know, to have the opportunity to watch it. I definitely want to watch it too. And there are going to be a number of places you know, to go and share that experience. This is one of those really cool shared experiences that we should all have. So find your favorite live stream to watch the launch and watch it. This is the first sort of real Falcon Heavy launch, you know, where they're actually putting a satellite up, you know, that's going to operate and everything else. They're going to land, you know, the two back on land, and then the central core one is going to be landing out in the ocean on a platform. So hopefully that'll all go well. Maybe it'll be postponed again. Who knows? So stay tuned, and I'll try to keep you updated in terms of this live stream as well as I possibly can. But you know, if it launches on time, definitely count on this live stream starting probably a little bit late. So yeah, that's just how it's going to go. So all right, everybody, take care. Have a great evening, a great day. Make sure to subscribe. Thumbs up if you so desire. Spread the word. Spread the word. That is my big message. We're trying to find our people, and I think we will. And so far, so good. I've got a great group here, and it's a lot of fun. So, all right, until tomorrow, I will see you later. Live long and prosper.
Live long and prosper. Have a good night.
All right, see you later. Bye.